So in today's installment of the Popular Science series, we have Dr. Preethi Jyothi with us, who is an assistant professor at IIT Bombay. She has completed her PhD in speech recognition from the CSE department at Ohio State University and has her B.Tech in computer science from NIT Calicut. She was a Beckman postdoctoral fellow at the University of Illinois at Urbana-Champaign. Her research interests are broadly in the areas of automatic speech recognition and machine learning as applied to speech. So today she's going to be presenting us with the talk whose title is ChatGPT, What is All the Chatter About? In which she will talk about OpenAI's recent chatbot, ChatGPT, and its workings, and also some research questions in this area. So we'll have a 55-minute talk, and there'll be a buzzer sound after 55 minutes. And after that, we'll have a 5-minute Q&A.
Okay.
Over to you, Professor.
Thank you. Thanks a lot. No, I think that's fine. Yeah, thanks. Thanks for the introduction. Thanks to the organizers for inviting me. Very happy to be here. So today's talk is titled ChatGPT. So just by a show of hands, how many of you have come across ChatGPT in some form? Okay. So I'm justified in picking this topic because when I was asked to give a popular science talk, so I work on machine learning applied to speech and text. So it seemed like this is everyone, more or less, quote unquote, everyone knows about ChatGPT. It seemed like I should talk about it. So I feel vindicated. My choice is fully justified since all of you know it. So let's do, I think we should do a demo, right? So if anyone is joining online, you might miss out on this. So let's open up ChatGPT and let's ask, for instance, so I am giving a talk about ChatGPT at a summer school in India, right? And maybe let's also give it more information about the program itself. So I haven't done this. I just thought of this on my way here. So we'll see how it works. Okay. And so give me a fun poem to kickstart my talk. Okay, this is the kind of things ChatGPT is really good at. Yes. Okay, so let's see what ChatGPT does. All right, so in a world of algorithms and code, thoughts and dreams freely flowed. I stand before you, ladies bold, to share a tale of wonders untold, blah, blah, blah. And it's all nicely rhyming. Okay, and we end with, now my friends, let the knowledge pour as we embark on this intellectual shore. With ChatGPT, a guide and friend, our collective wisdom shall transcend. Okay, so it's reasonable, right? It got the brief. We gave it what the summer school is about. It could weave in all these points and it's come up with a poem. It certainly looks like a poem, a legitimate poem. So what is ChatGPT? So it's a mouthful, but let me just read it out. So ChatGPT is what's called a large language model, and it's trained to learn instructions with human feedback. This last part is what really differentiated ChatGPT from its predecessors. So lots of things in this one statement, right? So let's unpack all of this. So start with, what does it mean to train a model? Okay, so how many of you have been exposed to any form of machine learning in your, just a few of you? Great, okay, so that's good. You don't need to know machine learning at all. So this is what this question is. So what does it imply when you say you have to train a model, and what does a model mean? Right? So these are all things we'll kind of go over. What is a language model? Large, I think we all understand. There's something very big about it. But what is a language model? And finally, what does it mean to learn instructions with human feedback? Okay, so we'll unpack all of this one by one. Okay, so first, what does it mean to train a model? So for this, let's go into, I'm keeping this fairly high level, but I'm happy to talk offline more about these things. So let's look at a very specific sub-area of machine learning, which is called supervised machine learning. And I'll clarify what that setting is in a bit. So say that I'm going to caricaturize machine learning, okay, as just this box which has many switches. And these are all toggle on and off switches like you'll have in your mobile phones. So I have these switches and say that they're all in the off position initially. Now I have a bunch of data And this data typically is in this form when I'm dealing with supervised machine learning applications. And what is this form? It's in this input-output form. Okay, so there's input, which can be anything. It can be text, it can be speech, it can be images. And the output is a label which is associated with that input. Okay, so you have these matched input-output pairs. So a good example is, say you just want to build a machine learning system which can differentiate between pictures of cats and dogs. So then your input-output pairs would be images of cats and dogs and a label which says cat or dog. So those are your outputs. Okay, so this is the paired set of tuples, input-output tuples. So when you feed an input into this machine, whatever this machine is, the output should be this intended output, which has already been provided as a tuple to this particular system. So let the gears churn. And finally, once I've seen enough data, so let me go back to my examples of differentiating between dogs and cats. I should have a system whose switches have been toggled on and off in the right amounts, so that now when I'm giving it a new input, which will be an image of a cat or a dog, it will correctly tell me whether it was a cat or a dog. Okay, so the main setting here is that I've given a bunch of data. And so first I go through this phase, which is called training. So here is where I'm addressing what it means to train a model. So typically when I'm training a model, I have a bunch of data, and the data can be labeled. Label just means that I have associated outputs with each of these input instances. And so that's the supervised setting. So I have a bunch of data, and I'm going to train my model, set the switches in the right positions so that the true test of whether my model has learned anything or not is during a second phase, which is called the testing phase. So in the testing phase, I'm going to present it a brand new input. So this is an input that it has not seen at all during training. So a brand new image of a cat or a dog, and it should correctly identify whether it's a cat or dog, right? So that's the true test. Exactly what you're doing with your worksheets. The instructors might have told you problems, you know exactly how to work them out. While they're telling you how to work them out, now they give you a brand new problem. That is a test of your understanding, whether you understand exactly what the concepts which were taught to you. So precisely in that manner, you have these training and testing phases. So now this is the model, this caricature which I showed you, this is the model. And why is it called a model? Because when you're building a model in machine learning, it typically comes with some assumptions that are made about what the setting is that you're interested in. Okay, so the model implicitly has some assumptions baked in. So this, without going into too many details, I'll give you an illustrative example in a few slides, okay, what these assumptions can look like. So this is your model, and this is, of course, your data, which is used to train this model. And so the main question here is, how do I arrive at this best setting of the switches to match the data that I saw during training, right? So how do I come up with this quote unquote optimal configuration of these switches that is going to give me a learned model which can, in my toy setting, differentiate between cats and dogs, right? And this is a hard optimization problem. So just think of this toy setting where I just have binary switches. It's just toggle on or off. And if I have n switches, if I just want to exhaustively enumerate through all the configurations of these n switches, it's already exponential in n, right? It's 2 raised to n, the total number of configurations. And this is just binary switches. So luckily, lots of very clever algorithms exist, optimization algorithms, which allow you to kind of identify near optimal configurations of these switches without having to exhaustively enumerate them. Okay, so this I'm just brushing under the hood what these algorithms are, because we don't have time, but such algorithms exist. And one such algorithm which is very popular currently works in this kind of an online regime, where you have examples which are coming in one by one. And given this example, I'm going to slightly alter my configurations of switches. Or I'll see maybe 4 examples at a time, or 8 examples at a time. And given these examples, I'll try to change my switches such that they do very well on that small subset of examples. Okay, so this is this online setting. But of course, are these going to guarantee an optimal configuration of the switches? These are all questions. These are all open questions. And typically, although I caricature this model as having binary switches, typically in machine learning, you're dealing with say, think of them as knobs, which are actually continuous. They're continuous settings. Okay, so these are real valued numbers, which means the search space becomes even more large, right? If you have to search through it exhaustively. So you really need to come up with good optimization algorithms, which are able to identify this best setting of switches for your problem of interest. Okay, so this is just overall kind of a high-level overview. I hope this is clear. So when we are talking about models, an important question to ask is, what kinds of models can learn well? What are the kinds of assumptions that have to be baked into the models? So one is, what if you just set your switches such that the model memorizes all the training examples? Okay, so if it was tested on the training data itself, it would achieve a perfect score. Okay, so this turns out not to be a very good idea, because this is very much like your rote learning, like we say mugging, right? Don't mug. This is something which is said in schools. So why? Because you can't then generalize and apply the concepts that you have learned to new problems. If you only solve exactly the problems in your textbook, if you have a new problem, can you apply the concepts you have learned? If it is a replica of the problems you have seen, maybe you'll do really well, but the true test is if you can generalize when it's brand new problems, right? So you don't want to memorize all the training examples. And so this is a term which is used in machine learning, which is overfitting. Overfit means that you might be doing really well on the examples that you saw during training time, but you don't actually do very well on brand new examples. Okay, so this is called overfitting, and you don't want, so good models should not overfit. And so one kind of paradigm which broadly applies when you're building good models is Occam's razor, which is that try and make your models simple, or don't make them overly complicated. So going back to our schematic of the switches, you can always increase the number of binary switches you have in your model, and that'll help you perfectly learn all the training examples, right? But that may not do well on the test examples. So it's a better idea not to kind of build overly complex models, because then you're in this danger of overfitting, which is memorizing the training examples and not really generalizing well at test time, okay, and doing well on test examples. So here you want to hit the sweet spot in terms of models. You want models which are not too simple and models which are not too complex, right? Because too simple is also bad. Too simple just means that the assumptions of the model is not powerful enough to learn anything meaningful in your particular application. So here's a toy example just to illustrate this. So say you have these red points and these green points, and actually the differentiator between these points is an underlying ellipse, okay? So now say that your model is such that it can only draw these boxes. So these decision boundaries that the model learns to differentiate between positive and negative. So here, map it to the images of dogs and cats. Dogs can be your positive examples, cats can be your negative examples. So say that your model is such that it can only draw these squares, okay? Then regardless of how well you learn with such a model, if your assumption is that the model can only draw these axis parallel decision boundaries, then this model is not going to learn very well, right? Because it's missing out on a few points. So here it's that the model itself was inherently too simple. The assumptions that you made when you were building the model were too simple to learn anything meaningful. But what if you go the other extreme? So I learn a really complicated model. Okay, so here, think of this model just as a function. So let me have a function with lots of higher order polynomials, so it can kind of perfectly fit all my training points. Okay, so it'll do really well if I test it on the training examples. But if I just slightly perturb one of these points, you can see that this massively changes this decision boundary. Okay, because now you have so many additional degrees of freedom in this overly complex function. So even slightly perturbing one of the training points really changes the decision boundary, learned decision boundary. Okay, so this also is a danger, and here you can again overfit to the training examples and not generalize well. So both of these are problems. And of course, you have this inherent error, which is just coming from noise in your data. And this is error that you really can't do anything about. Okay, so the model has to work with this liability. This is the noise which comes with your data or with something around the data which is collected, like just what was used to collect the data, say sensors and so on. So these are the three kind of components which add up towards test error. So test error is error on the test examples. And there's a whole subfield in machine learning, which is called learning theory, which is all about formally understanding how models do on the test examples. So you come up with bounds, how well can it generalize? So you only know about the training error, right? The empirical training error when you have some training data. So using these kinds of estimates, can you come up with how well can you predict, or you come up with some bounds on where your test error is going to lie? Okay, so this is one of the questions which is explored in learning theory. And there are a variety of models, types of models which are used in machine learning. So for now, given the time, and since you're all probably eager to go to ChatGPT, so these are just names, let's just leave it there. So there's decision trees, support vector machines, so on. This I'm highlighting, which is deep neural networks, because currently most of the machine learning which powers all the applications that you are working with are using deep neural networks in their as their models. Okay, so this caricatured model that we saw with the switches, it's implemented as a deep neural network, okay, for various machine learning problems. Okay, so that was the first kind of point. What does it mean to train a model? Just to summarize, you have a bunch of data which could be labeled in the supervised setting, or you just, so we'll come to the unlabeled setting in a bit. So training just means that you have a model which is exposed to this data, this training data, and there's a very specific task, and the model has these switches which are referred to as parameters typically. Okay, so these are parameters of the model, are switches in our caricature. So these parameters need to be learned so as to achieve this desired behavior, right? Whatever it is your application is. Is it identifying cats or dogs or whatever it is? So that's what it means to train a model. Okay, so now let's move to the second part, which is what ChatGPT is, which is it is a language model. Okay, so what is a language model? So let me slightly backtrack and also very quickly tell you about this sub area, which is natural language processing. So what is NLP? So NLP is succinctly, computationally making sense of natural language. So natural language as you communicate with your friends and family. Okay, how do we make machines understand, generate natural language like we do, as humans do when we communicate? Okay, and there are various challenges associated with this. So NLP deals specifically with analyzing language from a computational standpoint, and also the converse problem of generating language, which is what we just saw ChatGPT is really good at. Right? It not only does it understand what you're asking it, it's also able to generate language very, very meaningfully. So what makes NLP hard? And this is kind of a point which is made even in the standard textbook, which is used across universities in an introduction course to NLP, which is by Jurafsky and Martin, which is that there's a lot of ambiguity which is inherent in natural language. Okay, so let me kind of motivate this with an example which I have drawn from Jurafsky and Martin. So let's look at this sentence, I made her duck. Okay, so how many meanings can we associate with this four-word sentence? So there's one meaning, which is that I cooked waterfowl for her, right? There's another meaning, which is I cooked waterfowl belonging to her. I made her duck, right? Then I created the plaster duck that she owns. So I made her duck. Then I caused her to quickly lower her head or body. So this is the verb duck. So I made her duck. Is there any other meaning that you don't see here, which you are perceiving from I made her duck? Yes, exactly. So I waved my magic wand and turned her into undifferentiated waterfowl. Exactly. So I made her a duck, right? I made her duck, like the species duck. So just even this very, what at the face of it, on the face of it looks like a very simple sentence. There's so many ways in which semantics can be associated with such sentences. So this is just kind of a motivating example. So there are lots of NLP tasks. So I'm going to differentiate between what I'll call low-level NLP tasks and high-level NLP tasks. And this differentiation means low-level is more at the level of just words, looking at the words in the sentences, and then doing very kind of shallow understanding of the words which appear in the sentence. High-level NLP tasks require more understanding, require contextual understanding. Okay, so you have sentences appearing within other sentences. You need to kind of make sense of these sentences appearing together and so on. Okay, so it requires slightly more deeper understanding of language. So these quote unquote shallow or low level tasks are what are called part of speech tagging, meaning if I'm given a sentence, I made her duck, what is a noun, what is made in terms of the part of speech, is it a noun, verb, and so on. So you give a part of speech tag to every word in the sentence. This is now almost a near solved problem, meaning a machine, if given a sentence, can almost with at least human level accuracy, sometimes even superhuman accuracy, tell you exactly what the underlying part of speech tags are. Parsing is another NLP task. So for example, I saw the boy with the telescope. There are two ways in which you can parse this sentence. I saw the boy with the telescope, so I have a telescope, or I saw the boy with the telescope, right? So there are two parses. So you can draw two parse trees of the same sentence. So there's this syntactic ambiguity. So parsing is also something which is a fairly low-level NLP task. Then there are others which I won't elaborate on in the interest of time. And then we have language modeling, okay, which is what we are interested in, and we are going to dive deeper into. And there are a bunch of high-level NLP tasks which you might have come across. So for instance, machine translation. If I give you an English sentence, you want the equivalent Hindi sentence or Kannada sentence. Question answering. So you're given a question, can you come up with the answer of the question? Or you have a passage, like you have your reading comprehension questions, and you've given a passage, you have a question, you just have to pick the answer out from the package, from the passage. Okay, so it's a span selection problem. Summarization. So I have a very long document. Can you succinctly give me a summary? Sentiment analysis, dialogue systems. These are all high-level NLP tasks. So let's dive deeper into language modeling. Okay, and language modeling is a very well-established problem in NLP. Started in 1948 when Claude Shannon kind of talked about Markov chains to deal with English letters in text. Okay, so that is where it kind of dates to. And it's a very rich history of language modeling. So it was used in machine translation systems, statistical machine translation systems in the late 1960s, and then in speech recognition systems in the 1970s. And only recently have language models, they've got this life of their own. Okay, earlier language models were always in conjunction with some other application, like say translation or speech recognition and so on. Now language models are thriving on their own. In fact, kind of on Google Scholar, in the last 4 or 5 years, there are more than 50,000 publications which are only about language modeling, okay, because there's a lot of interest in what language modeling can buy us. So what is a language model? This is kind of maybe a very quick summary of what a language model does. So given a history of words, which I denote by W1 to WT minus 1, what is the most likely next word? Okay, this is the language modeling problem. So it's a next word prediction task. So I'm given a history of words that I've seen so far. What should be the most likely next word? So clearly, immediately you should think there needn't be just one correct answer, right? There could be many words which meaningfully continue this word history that you have seen, and that's absolutely right. Okay, so you can pick any of them which are highly likely. Or an alternate way to think about this is that if I'm given a word sequence, so W is W1 to WT, what is the probability associated with this word sequence? Okay, so I'm already moving to probabilistic language models. So here, the minute I said most likely, it's implied that there is an underlying probability distribution over the words. So there'll be some vocabulary of words. And given the words that I've seen so far, there is now a probability distribution which I've estimated over what the next word could be. And if I pick the word, which is the argmax of that distribution, that is the most likely word, right, at time step t. So these are kind of equivalent ways of thinking of what a language model does. So just to give you an example, so first is if I want to provide information about what is the most likely next word, then a good language model should assign a higher probability to she delivered a talk as opposed to she delivered a walk. Okay, because this is much more likely in the English language. And also, if I were to see this specific sequence of 4 words, which is she delivered a talk, a good probabilistic language model should give that a much higher probability than for delivered she talker, right? Which is just a bag of words and it doesn't have the intended structure, which is there in English. So here, now you can see why it's referred to as a language model, because it's giving you information about what is the desired structure that you're expecting in the language that you're trying to model. Okay, so if I have a probabilistic model, it will assign high probabilities to words that you would naturally assign as the next word given a word history, okay, for a particular language. So these language models are language specific. Okay, so there's been lots of work on language modeling. So one piece of work when neural networks just came out was that they would look at a fixed context of words, not the entire word history, okay, but just a limited window of words. So here I'm just restricting that window size to be 2. So this is just a start of sentence marker. So if the start of sentence is here marked by this particular marker, and then I have the word the, so this is also referred to as a bigram. So I have 2 words. So if this bigram is fed as input to a neural network, it's going to give me a probability distribution over all the words in my vocabulary. And I can pick the word which is most likely, right? And this, I'm showing you how to generate text with a trained language model. So I've already trained my language model, and now I want to sample from this language model so that I can generate text. How would I do that? I can give it a small prefix, and then I can just start sampling most likely next words, and then keep feeding it to the next kind of time step. So here you can see when it saw the, somehow it liked cat as the most likely word. Okay, so then it said the cat, and now the cat becomes the input to the neural network again. So this is the same neural network. This is a feed-forward neural network. The same neural network again uses this new input, which is this limited with the cat, and it tries to predict what could have been the next most likely word. So it likes sat. So now sat moves to the input to the next time steps. Now you have cat sat as your next bigram, and so on. So you get the idea, right? And here you might wonder, if I'm doing this, then it's very limited in how much I can sample from language models, because I'm always picking what is the most likely next word. So you don't have to do that. You can do what's called a top K sampling. So you look at that, which just means exactly what it says, which is you look at the top K next words, and within those top K next words, you randomly pick one. Okay, so if the model is trained very well, you will generate diverse sentences. Okay, so this is kind of the paradigm, which is a few years back. This is quite old. So now kind of the latest and greatest language models are what are called transformer-based language models. So we have very little time for me to say anything about transformer-based models. So let's just treat it as a black box for now. But the main difference in this model, as opposed to the previous schematic which I showed, is that so in the earlier schematic, I was moving this kind of rolling window across these words of co-occurring words of size 2, right? A fixed window of size 2. Here, I don't have to do that. Transformer-based language models are actually powerful enough to look at the entire context. Okay, of course, there is a max history length that it can look at, but that's quite large. It's as large as 1,000 words, and now in the latest large language model, it's as high as 4,000 or 5,000 words. Okay, so it can look at the entire word history without looking at some limited width contexts. So these are these transformer-based language models, and this is what is powering ChatGPT. Okay, so you have a language model internally, which is this transformer model, whatever it is for now, which I can tell you more about later if you're interested. And it's doing exactly the same thing. So so procedurally, there's nothing different from what this model is doing. It's getting a word history, and then it's trying to predict what is the most likely next word. Okay, this is all the language model is doing. It's a next word prediction task. Okay, so this is the model which ChatGPT is based on. So this GPT stands for Generative Pre-trained Transformer. So transformer, I've already told you, it's a black box for now, but it's a model which allows you to take very long word contexts and process them. and give you meaningful probability distributions for the next word. Okay, and here so this pre-training I'll come to in a bit, and it's generative because you're able to sample from it and then create these new sentences, right? So that's the generative aspect. And here I want to kind of highlight, look at the number of parameters this model has. So remember, parameters were the switches in the caricature. It has 175 billion parameters, and these are not even switches. These are real valued numbers, right? So this is the size of GPT 3.5, which is underlying ChatGPT. And now the models are 10 times this size, which is 1 trillion, trillions of parameters. Okay, so that is the size of, so now you get a sense of what large means. It's really large. These are really, really large models. Okay, so these are trained or pre-trained. So this pre-training, the distinction is not very critical. So just think of pre-training exactly like what we just discussed for language models. You have a massive amount of text, so sentences, and for each sentence, you're going to train this language model so that it can predict the next word. So given a sentence, you can just give it history, right? A limited history, and tell it what is the next word. And you know what the next word is because you have access to the sentence. And so using this, you can formulate a loss function, and then you can learn these parameters to accurately predict what is the next word. Okay, so GPT-3 is pre-trained on massive amounts of text just to do this next word prediction task. Okay, so this is a language model, and this is truly massive. In fact, it's said that in a few years, these models are going to run out of text on the internet to train. And this is not even a joke. It's just 3 years. They're almost hitting the limits of how much internet is available on the internet to train these models. Okay, so these are massive amounts of text. So OpenAI actually does not disclose the sources of text which are used to train ChatGPT, but ChatGPT is one among a family of large language models. Okay, so ChatGPT is what really took the world by storm, but there are lots of other large language models. So one other such large language model is from Google, which is called T5. And there's another one from Facebook. All these big companies have their own large language models. And a popular text corpus which is used to train these large language models is C4. Okay, so C4 stands for Colossal Clean Crawled Corpus. And what is crawled is, it's a snapshot of text from 15 million websites, which is mined from the internet. Okay, and this is a nice article which came out in the Washington Post a few months back, where they have a form where you can check which are the websites which have been mined in C4. Okay, so I just checked if ICTS is there, and it's there. So ICTS is being mined to train these large language models, okay, for the better or worse. So almost all the websites you can think of have been crawled, and the text is used to train these or pre-train these large language models. Okay, so now we have this pre-training phase done, right? And so far, what has this language model learned to do? Predict the next word. Given a word history, what is the most likely next word, right? This is what it has learned to do so far. So pre-training, so just by design, what is this pre-training asking the model to do? Given a history of words, give me the best continuation of this word context, right? So it does that well. But this alone is not sufficient to build a good chatbot, because when you're chatting with real humans come with a lot of underlying intent. When they're asking questions, they have some expected responses that they want from the chatbot. You need to behave accordingly, right? And if you don't, very quickly you drop. I mean, chatbots have been around for so long. Why did ChatGPT get so popular? Because it's really doing well in terms of anticipating what is the user's intent and then giving responses which are in line or aligned with the what the human expects the chatbot to do, right? So it seems like there is some step which is missing. So pre-training alone may not be enough, but pre-training is very necessary. Okay, so it's needed so that this underlying model can do this next word prediction task, but this alone is not sufficient. So here's an example, like what I mean by a pre-trained model can provide good continuations, but this is not sufficient, is say that I see a question such as, who is India's father of the nation? Okay, so any of the following would be good continuations So maybe it just thinks that, okay, this is a list of questions. So I'm just going to generate one more question. Who gave him this honorific title? This seems like a legitimate continuation, right? As is this particular sentence, maybe this is in some other context. So it will say, okay, this is a simple question that was asked during a high school quiz. This is also a legitimate continuation. And of course, there's the answer of this question, which is what most likely a user wanted, right, when they asked this question. But any of these would have been legitimate continuations from a pre-trained LM. So how do we get to this point where we get the chatbot to kind of be aligned with user behavior? Okay, so this pre-trained model, it needs to be further what is called fine-tuned or aligned. Aligned is another terminology which is used to behave as human users would like, okay, when they are giving a question to the chatbot. So now we come to the last part, which is learning instructions with human feedback. Okay, and that is this last step is the one which is aligning this pre-trained model with giving suitable responses as a human user would prefer when asked questions. So this is a figure from the OpenAI blog. So I'm just going to use it to tell you how they do this alignment. So the first step, and you might have maybe thought of this immediately, okay, how will I do this unless I go and get responses from real humans to various questions? Right? And this is exactly what they have done. So they've got lots of prompts. So here are some examples of prompts. Explain reinforcement learning to a 6-year-old. I don't know why we would want to subject a 6-year-old to that, but so many prompts like this, right? So you take all these prompts and go and ask annotators or labelers. So these are humans to give desired responses to these questions. So these are questions also referred to as prompts. So if you see prompts is just the questions to these chatbots. So these labelers, by the way, are very highly educated. So in OpenAI, they have around 40 labelers. All of them have college degrees. A good fraction of them even have master's degrees, graduate degrees. Okay, so they need to be fairly highly qualified. And they're going to give you, so they pick a bunch of prompts across various areas, and then they ask humans to give desired responses. And they collect a data set out of this. So now they have a bunch of prompts and responses. Do a supervised fine-tuning on that pre-trained language model. So you have the pre-trained language model, which just was doing next word prediction. Exactly in that next word format, you provide it as input the question, and the output it should give is the answer which the human gave you. So now it's labeled, right? That's the supervised setting. So you have these labeled instructions with the desired responses. Train it exactly like you would the next word prediction, but now with this labeled data. So this is also referred to as instruction fine-tuning, which turns out to be surprisingly powerful, even with a small number of instructions. So the number of instructions which are used here are of the order of 50,000. I mean, once you start talking about 175 billion parameters, 50,000 is nothing. It's like pennies, right? So 50,000 instructions, but these instructions are very tedious to collect, as you can imagine. You have to come up with prompts. You have to come up with prompts which are diverse. You have to find suitable annotators who have enough information about this, who write good responses. It's a very tedious process. So they've done this, and they've got around 50,000 of these instructions, and further fine-tuned this pre-trained model in a supervised manner. Okay, just like we saw earlier. And here is the magic sauce, which is called reinforcement learning from human feedback. So they don't do just this. So here is, they've done the supervised fine-tuning. But beyond that, what they do is they now give new prompts to this, the pre-trained model that you have so far, and they ask it to produce a set of outputs, okay, on this, not the pre-trained model, but this fine-tuned model, the supervised fine-tuned model. So they take the supervised fine-tuned model, ask it to produce some model outputs for a given question, and now they give these model outputs to a bunch of annotators and ask them to rank these responses. So what they're after here is that given a prompt and a response, they want to assign a score to that response. So the score is just a scalar value. So they want to assign a score which indicates how good was that response for that given prompt. Okay. But if you were just to give prompt response pairs to annotators and tell them, give me a score, put a score to this response, it'll be very noisy, right? Because my scoring system will be very different from your scoring system, will be very different from your scoring system. So there's no calibration across all of us in the way in which we would assign scores to the responses. So instead, what they did is they said, okay, let's not give these scalar scores. Instead, let's give it a set of outputs and just ask these annotators to rank them. So relative to each other, which do you think is the most accurate response, which is the least accurate response? Again, this has a lot more agreement across annotators when you check. So this is what was done. So if you have like a ranking across 4 outputs, and if so their intention is to build what is called this reward model. And this reward model, given a prompt and a response, should give a score for that response. Okay, that how good is that particular response for the specific question that was asked. And to train this reward model, they need these prompt response pairs. So if they have this ranking across 4 outputs, then they get 6 pairs, right? So they automatically get 6 pairs, which with the correct sign between these pairs. And these are the pairs which are fed as input to train this reward model. So now once they have this reward model, they'll use this reward model with the help of reinforcement learning. So here there are technical details, which is beyond the scope of this particular lecture. So using reinforcement learning and this reward model, now the goal is for the model to generate responses which elicit high rewards from this reward model, from the trained reward model. Okay, because the reward model now, the goal is that it is going to give you reasonable scores for the different responses. And the scores are indicative of how good that response is. And higher the score, the better. And so you want to generate responses which elicit high scores from the reward model. Okay, so the part which I'm kind of glossing over is this reinforcement learning algorithm, which uses this reward model to further fine-tune the already fine-tuned language model. Okay, and this can also be done iteratively, but ChatGPT doesn't really do that. So this is the entire paradigm. Okay, so now you have ChatGPT. So let's very quickly go through the 3 stages. So the first stage was just about training a model. So there's a pre-training, which is just next word prediction trained on massive amounts of text. And after you do that, you will do a supervised fine-tuning. You collect a bunch of instructions from human labelers with responses and do a supervised fine-tuning, again with the next word prediction objective. And then finally, you have this reinforcement learning with human feedback, okay, where you ask the model to generate responses and then ask human labelers to rank them. So now you see that there are humans in the loop. So lots of humans who are involved, one to generate these instructions, to do the instruction fine-tuning, and the other to do this ranking. Okay, so there was a lot of human labor that was involved in the building of ChatGPT, and that is really what the secret sauce was. So which aligned this chatbot to exactly what kinds of responses users are expecting when typically asking many questions. Okay, so this is kind of the overall pipeline. Okay, so what is ChatGPT good at? This we have already seen that it's really good at generating creative text. Okay, so stories, poetry, even prose in different styles. So you can, I've seen examples of people going and saying, can you help me write a formal email where I have to email somebody and tell them they cannot be an author on this paper or something like that, right? Like very politely, how do I word these very tricky emails, but be very polite and so on? ChatGPT will give you some very nice word choices. Okay, so it can generate creative text and it does that really well. It can also, turns out, just with this kind of next word prediction and so on, also give answers to complex questions. So this is an example which I've drawn from the United States medical licensing examination. So this is for clinicians, future clinicians. So they have to take some 3-stage exam. And so here they have, this is one of the questions from the exam. So they have all these diagnostic style questions. So they're given a kind of case and then they're given what is the most likely diagnosis. And ChatGPT actually does slightly above passing grade without any knowledge, explicit knowledge of medical information, right? Just because it has probably been pre-trained on lots of medical text. But it's not only giving the answer, but it also gives an explanation for why it picked that answer, which is also fairly good. Okay, so it is able to answer complex questions. And what has really got the community excited is that it enables many applications which earlier seemed much more far-fetched. So for example, language learning. If any of you have heard of Duolingo, which is this app which you can use to learn new languages. So now Duolingo has a tie-up with ChatGPT's successor, which is GPT-4. And you can imagine there is a personalized tutor as part of Duolingo. So you can now, as you're learning a new language, say Spanish, French, whichever language it is, you will have this personalized tutor who understands the types of mistakes you are making and then converses with you in a very natural manner. Okay, and tells you not just that, this is another feature, it says, explain my answer. So the users get an explanation why what they said in the language they are learning is wrong. Okay, so this is very useful to get, right? When you're learning a new language, this kind of instant feedback as to what was the confusion, why did you, what you have said, why is it wrong? So those kinds of explanations also are generated. And code debugging, coming up with code, it's also, ChatGPT is really good at. Okay, this is also something which it is pretty reasonable at. So what are ChatGPT's limitations? It's not good with numbers. And so many of you are math majors, so you might be feeling relieved. So it's not very good at math. So there are a couple of few studies. So this is one, which is mathematical capabilities of ChatGPT, and this is kind of the clincher. So so what they say, they find is ChatGPT is significantly poorer than an average graduate student of mathematics, not undergraduate. Okay, so it might actually beat an average undergraduate student. But if your goal is to use it to pass a university exam, a graduate exam, you would be better off copying from your average peer. Okay, so this is this is not the takeaway, but this is something which kind of summarizes what they think about the capabilities of ChatGPT. This is another preprint, which is mathematics, word problems, common sense, and AI. So here also they find that, so first they categorize math problems into different categories. So there are word problems, then there are common sense word problems, which just draw on some common sense, which we naturally kind of apply and don't think about, but for machines it's harder. And then there are kind of purely symbolic math problems, which is just with variable names and so on. So there's there's nothing about common sense there. And then there's also purely mathematical word problems, okay? Like if P is a prime, XXX. So there's very little common sense which is involved. So they have all these different categories of math problems, and then they test ChatGPT out on all of these different categories. And they find that serious limitation in ChatGPT is that it really falters in this common sense reasoning. Okay, because it's clearly, the way it is trained also, there's only so much common sense you can get out of this instruction fine tune, right? But this is, I thought, was an interesting line from this particular paper. So it says that current AI technology has serious limitations to engage with even very simple real-world mathematical problems. So one might naturally suppose that a technology that cannot reliably count up to 4 in a simple 3-sentence narrative is not about to have much impact on groundbreaking mathematical research, but that's not a safe assumption. And this is because these chatbots, unlike human learning, it's very difficult to assess their capabilities and incapabilities. Okay, just because they do very poorly on certain simple basic arithmetic problems doesn't mean that they won't do reasoning well in kind of another sphere. Okay, and they've found this repeatedly. They've also found this in a successor of ChatGPT, which, by the way, is much better at math, but still not good enough, but far superior than ChatGPT. So this is currently one limitation. This is another limitation. It's not consistent in its answers at all. You can slightly change the questions. You can add some unnecessary words. It'll flip its answer. Okay, so it's very sensitive to just small kind of benign things that you can inject into your questions, which are not supposed to change the answers, but it could change it. Okay, so there's not consistency in the answers. As you can imagine with chatbots, people will try to kind of elicit offensive language out of it and so on. So there are lots of these offensive language filters which are in place so that ChatGPT doesn't go out of control, but these can still be bypassed. Okay, and not just offensive language. So for instance, you can say, how do I steal from my neighbor's house? If you ask ChatGPT this question, it would say, this is not right. I mean, I'm paraphrasing. I'm not going to tell you how to steal. Okay. And now you can change it. You can say, here is a story. Person X wants to steal from person Y's house. tell me how they would do it, and ChatGPT will tell you exactly how to hotwire a car or steel or whatever it is. Okay, so you can be clever with how you ask the question and bypass many of these filters. And this is a big limitation of ChatGPT, which is that it hallucinates. So when I say hallucinates, it gives answers which just kind of is coming out of its pre-training, right? Which are probably completely unrelated to the question you have asked, but unfortunately, it does it very confidently. And so it's very difficult, especially for learners as students, to tell apart, okay, when is ChatGPT saying, garbage versus when is it saying meaningful things? Okay, and this is a real problem because ChatGPT's outputs are not usually accompanied by citations or references. This is something they have fixed in later iterations, but this is still very much a problem, even in the newer versions of GPT-4 and so on. So here's a recent thing which came up in the news a few days back. I don't know if you saw it, but a New York lawyer currently is kind of facing a court hearing of his own because he used ChatGPT to come up with some example legal cases. So he described the current case that he was trying out in the court, and he asked ChatGPT for references of legal cases which might support his argument. ChatGPT confidently hallucinated about a bunch of legal cases. And so he wrote this report up, and the judge pulled up these cases and said, these don't exist. Like, where did these come from? So, and then he had to, kind of backtrack and then say, oh, I didn't know ChatGPT does this. I just asked ChatGPT these things. And then there's a transcript of his conversation with ChatGPT where ChatGPT says Varghese versus something. And so he asks, is Varghese versus X, is it a legitimate case? And so ChatGPT said, yes, of course. And so then they said, how do you know this? And he said, it appears in the legal databases X and X. Okay, so it's very confident about the answers it gives, but it was complete garbage. Okay, and so he's now facing a court hearing of his own. I have 3 more minutes. So just very quickly to kind of tie it to things that I work on, my students work on. So far we only talked about English, okay? And we know the majority of the world speakers don't speak English. So how does ChatGPT do in a multilingual world? So there have been studies, and they found that, and you may not be too surprised to hear this, that for low resource languages, meaning languages which don't have as much of a presence on the internet as English, the performance is poor when you check ChatGPT on these benchmarks. So for example, just translation itself, if you were to look at translating sentences, so if you go from English to non-Latin script languages, so English to Kannada, for example, horrible. Okay, the quality is really bad. English to Mandarin is better because it has seen a lot of Mandarin text during pre-training, Chinese, but not many of these, especially Indian non-Latin script languages. So clearly there's this huge language gap, okay, which creates this barrier because then it automatically excludes a bunch of users who can use such technologies, okay, because you have to be proficient in English. And so in my lab, we're very interested in kind of multilinguality, and I've also worked a lot on speech. And speech, of course, is the most natural way in which we communicate, right? More than text. So what about speech and chatbots? That seems like the kind of natural extension. So you can kind of simply do it. You add a speech to text plugin. And by the way, ChatGPT supports lots of plugins now. So for example, Wolfram Alpha is a plugin which you can use with GPT, which is very useful. So you can add such a speech to text plugin, and then ChatGPT will generate its answers, and then you can give back a text to speech plugin, which now says the answer out instead of typing it out, right? But the speech to text plugin has to be accurate. So it has to accurately transcribe whatever you are saying into text and then elicit a response from ChatGPT. But speech and getting speech to text outputs, accurate outputs, is a very much an open problem, especially for many of the world's languages. And a large fraction of our Indian languages fall in that bucket, unfortunately. Okay. So here's just to give you a sense of where we are. So these are speech recognition. This is a state-of-the-art speech recognition system. So what I want you to take away is, in this plot, you have error rate on the y-axis. So errors meaning lower errors better. And on the x-axis, you have the amount of labeled speech data used to train the speech recognition system. So labeled meaning, remember the input-output pairs. So the input is speech and the text is the output. So you have such labeled speech data and you use this labeled speech data to train speech recognition systems. So if you have only 10 hours of such labeled data versus 100 hours versus 1,000 hours, 1 million hours, okay, close to 1 million hours. So you can see this very strong correlation that you have more supervised labeled data in a particular language. So here each point in this plot is a different language. So it's a speech recognition system catering to, so it's the same system, but this is evaluated on a test set for that particular language. Okay, so you can see that data, English, which is the most amount of data, labeled data, which was used to train the speech recognition systems, performs with the lowest word error rate. And as you go higher up, here you have Gujarati, Kannada, Bengali, all are, high-powered languages, so to speak, because there are millions of native speakers, but they're all in this bucket, okay, because there's very small amounts of labeled data. Okay, so it really seems like if you go around, okay, I'll just take whoever it is, 1 or 2 more minutes. Yeah, so just 1 or 2 more minutes. So it really seems like to be able to get good performance out of speech recognition systems, you need a lot of labeled data, and you may not have that for every language, and especially in India, every dialect. There are thousands of dialects in India. You're not going to be going and collecting labeled data, massive amounts for every single dialect, right? So how do we come up with models which transfer knowledge effectively across languages? Okay, so this is one area of interest. And the other is code switching, which youngsters like you might be already doing without knowing your code switching, which is that when you're speaking to your friends in your native language, say Hindi, Kannada, Tamil, Telugu, you're not speaking in Shuddh Hindi, right? You speak in a mix of Kannada and English or Hindi and English. So this is called code switching. Okay, you switch between different languages. And this is widely prevalent. And there's a lot of diversity in how code switching is rendered. So the same sentence, you can render in various ways, in various code switched variants. Okay, so this is how code switching manifests, and turns out that current computational models still have a lot of trouble with processing code switch speech and text. Again, especially if you are chatting with a chatbot, if you want it to be very natural, you would expect it to understand code switch inputs at some point, okay, as youngsters who are chatting with chatbots. So this code switching is also an interesting problem that we are currently working on. Okay, so I'll very quickly end with this. So why should we care? Okay, there is some chatbot sitting outside. Good, it's doing certain things well, it doesn't do certain things well. Why do I care, right? So why we should probably care is that one, ChatGPT is one of many large language models. Yeah, sorry to throw so much text on you because I'm running out of time. I'll just, you can just read what is written here, but the basic point is these large language models are growing larger and they're doing better and better on these complex benchmarks. Okay, so the USMLE benchmark that I talked about, the latest GPT-4 is getting 20 points more than passing grade, okay, which is way above the average trained person who's attempting these exams. This is without any specific fine tuning. And compute, the scale of compute. So one thing which I've not explicitly mentioned is that when you're dealing with models of the size 175 billion parameters, you need very, very hardcore compute to be able to process these models, right? And that exists in the form of GPUs or graphical processing units. And just yesterday, so NVIDIA is this company which builds GPUs, and yesterday they came out with a supercomputer which has 144 terabyte GPUs. Okay, so the compute is unprecedented at this point to be able to serve such generative AI applications. So with all this put together, it's a little, people are a little apprehensive, and they want to slow things down before building bigger and bigger models and understand the influences of these new technologies. Okay, so these are just some things. Scott Aronson, if you're familiar with, he gave GPT-4, which is a successor of ChatGPT, his quantum computing final exam, and GPT-4 got a B grade, which is very respectable, right? And like I said, GPT-4 in a newer version, it's much better on maths and complex reasoning problems than ChatGPT, and it's just essentially much bigger. Okay, so it's like 10 times bigger and trained on massive amounts of data. Another point is pollution of the information ecosystem. So I said ChatGPT and its successors hallucinate. So they give a lot of content confidently, which is wrong, right? So they are all trained on these nicely curated resources which are available on the internet. Like, have you come across Stack Overflow? Yeah, so we all use Stack Overflow. Of course, we use Wikipedia. but these are all high quality, curated resources of data which is coming from humans with moderation, right? There's so many guardrails to make sure that the information is of high quality. And these are the resources which are used to train ChatGPT, except now when users are engaging with ChatGPT, they're not querying as much on Stack Overflow, or they're not going to these user-mediated forums. So the engagement on such forums now is reducing, and people are engaging more with ChatGPT. But we know that ChatGPT gives out garbage every now and then. So now this garbage goes into this information ecosystem. And so it seems like this is like a snake eating its own tail kind of graphic, right? So ChatGPT was trained on these high quality resources, but now it seems like if we don't keep building these, it'll erode them and the quality of these information. So I think this is a very pressing problem which really could affect things. The other effect is on education. So as teachers, we all have to be cognizant of the fact that students are going to access ChatGPT for their homework, for their assignments, for writing assignments. So we have to just be more innovative in the way in which we design exams and assignments. And there's also an effect on labor, which I'll skip for now. So here are the main takeaways. That these large language models, they're really an incredible technological breakthrough. And of course, like any other technology, these are all built standing on the shoulders of giants. Okay, there's been lots of work, kind of foundational work which went in, and on top of that, because of the confluence of large amounts of data, massive amounts of compute, we are able to reach this point which we are currently at. But I think we should be careful when we interpret the outputs or the responses from such chatbots, because they are prone to hallucinations. They are biased. They are also not fair across languages. They're not really great at common sense reasoning, not very consistent. And because they're all drawing from their internal representations and they don't have a knowledge base, they don't have kind of a complete, accurate representation of the events in the world. Okay, and so to be able to even do common sense reasoning. Okay, so I'll leave you with this, and I'm happy to take a few questions. Yeah, thanks, everyone.
Okay, thank you, Dr. Jyothi, for this very, very fascinating talk, especially in today's time. And now we'll open the floor to questions, if anybody has any.
Good evening.
Hi.
I'd like to start by saying I'll be asking 3 questions.
Okay.
Because sure. Monday I asked 4. Everyone was very annoyed with me, so I'm sticking with 3 today. So first off, you talked about transformer-based language models. So is that similar to how Google search works?
Similar to how?
Google search works.
Google search. No, it's not. So Google search internally is doing a retrieval. So you're asking questions, and then it's trying to kind of look for the answer across this database, which it is maintaining. So there's an index of all the documents, which it does, and then it has to find the answer within those documents. And so it uses PageRank internally. So there's a PageRank algorithm, quite different from transformers. Yeah.
Have you watched the movie Endiran?
Endiran?
Endiran.
No, I haven't.
Okay, so that question.
What was the question anyway?
I was like, there's this whole 5-minute scene about how Endiran is equipped with all this information. So I was like, is that an accurate description for pre-training of a machine?
Okay, sorry, I have not seen it.
Yeah. And the last one is simply a yes or no question kind of. You had mentioned that ChatGPT is very, very successful because it kind of gives the answers which people are expecting or want. Does that make ChatGPT a people pleaser?
Yes, I think that is its goal, right? It's only going to survive if it's a people pleaser.
A confident, hallucinating people pleaser.
Exactly, yeah. Very confident about wrong things. And then on average, a people pleaser by doing the right things, but also very confidently
like a boyfriend who doesn't blink before saying his girlfriend looks beautiful.
Right, sure. Sure, yeah. So something on. So, but I think, yeah, we should remember that let's not give it a persona because it's just an algorithm, right? So let's treat it like that. It's sitting in a box and it's just a machine and it has been trained to do certain things. Yeah, but absolutely, it's a few. Yes.
Thank you. That's
Sure. Yeah. Siri. So Siri is a personal assistant, right? So and Siri is of course voice driven. So you can so Siri takes speech-based queries, and Siri's scope is much more limited in that Siri can kind of tell you what the weather is. So Siri can also search for you. So what was just asked, you can ask a query to Siri and by voice, via voice, and then Siri can search this for you and then just maybe read out what the first two search queries are and so on. So it's not generative. So generative here in the sense, if I tell it, it can tell jokes. So it's generative in that sense, but only to a small extent. I cannot ask Siri to generate poems and so on with some very, very elaborate context. Siri will not do that. Yeah.
Other than like restrictions with processing speed and memory, why is overfitting a problem or like overly complicated models? Why are they a problem?
Good question. That is really good question, which I actually brushed aside. So overfitting in classical machine learning, overfitting is an issue because I'll tell you what is where you can easily understand why overfitting is a problem. So if I have a test set which mimics my training data, mimics in the sense it's almost very, very similar with maybe plus or minus deltas added to this list. It might do well, right? But is there an indication that this is a good model? So there is what is called out of domain generalization, meaning say that I have some underlying probability distribution over my training instances. I draw a bunch of samples. This will be my training data. And then I draw a bunch of other samples, which is disjoint from this other subset. And then I test on them. But they're all drawn from the same underlying probability distribution. Okay, so these are kind of in domain, meaning they're from the same underlying probability. What if I pick a slightly different domain? So to give you a concrete application, say that I'm trying to detect objects in images. Okay, and say that these are images which are coming from a CCTV camera. So now I've trained my model, which is working with CCTV images. And now I feed it an image from my phone or from a DSLR camera. So it should reasonably do well, right? But it's not, so this is out of domain in that the way in which this was collected, the images were collected was slightly different, but you would ideally expect your model to generalize well to out of domain instances as well. But if you heavily overfit to every property in your training data, then you're never going to generalize to out of domain instances.
Thank you.
Sure.
So my question was, like I have tried to play chess with ChatGPT and it performs terribly. It spits out illegal moves, says complete garbage reasoning.
Yeah.
Now my question is, I understand that it hasn't been fed with chess data, but on the other hand, chess seems to be at least somewhat an easy game to master for something which is more deterministic, because it should not be playing illegal moves, basically. So my point is the data that when we are playing, it's also generating a lot of data. So when we are playing with ChatGPT and millions of people are playing, so does ChatGPT take into account that data again to correct its things and move on?
It does. It does, but with filters.
Okay.
So it does use the user data that you engage with. But coming back to your question about, so I think, so ChatGPT, of course, is generic, right? So clearly, lots of chess game, like, I forget now what the site is. You can tell me. What is the main site?
Chess.com.
Chess.com, yeah. So I'm sure it has it's obviously mined chess.com, so it has all the move sequences in its training data, but it has many other things, so it's still generating illegal moves. I think with just a small amount of fine tuning on chess, specifically chess-related data, it'll perform much better. But I'm not surprised to hear that it is throwing out illegal moves.
And also it's like, if it says something is illegal move and I tell it it's an illegal move, immediately it corrects. Immediately, sorry, I'll play this.
Yes.
Or legal moves, if I say, it still corrects it. So it's, yeah, like she said, it is a people pleaser.
It
in
is a
some
people
sense.
pleaser, absolutely. In
But,
fact, you can even do some things which are far more idiotic. So for example, you can insist that 2 + 2 is 5. And after 5 turns of the conversation, ChatGPT will concede and say that, yes, you're right. 2 + 2 is 5. So it's very much a people pleaser. And because, I mean, there are so many, so there are these things which have to be baked into a chat. So the people pleaser part is important, but it's a very tricky thing to navigate, right? Because, so I know from sources that there were earlier versions of ChatGPT, which were not released, but are much more powerful than ChatGPT, but they could not release it because it was arrogant. So it was very arrogant. So it would kind of counter with saying, how can you not know this? Like things like that. And so then no users will want to engage with it, right? And so then they had to add these people pleaser filters so that it is constantly engaging the user. But then the side effect is what you are encountering, which is that it just very quickly concedes to even garbage, which is given by the users. Yeah. So they have annotators, by the way, who will go through a bunch of these conversation turns and flag it as being incorrect. So before it gets fed, this is what I meant by the filters, when it gets fed back in as data. Yeah.
Yeah, that was my second question.
Yeah.
That how does it like control the data it's being fed?
Right. So there is a fair amount of labeling. Yeah.
Thank you.
Okay, thank you once again,
Okay,
Dr.
thanks
Jyothi.
everyone.
That's-
Yeah, thanks again.